Today's lesson is going to be on fronts. It's important that we know the differences in characteristics between warm fronts and cold fronts. Notice in the picture below, a cold front is a blue colored with triangles, kind of a line that's got triangles on it. It's identifying a colder air mass is moving into a warmer zone or air mass, and a warm front is identified by red. You should be able to describe the clouds and cloud patterns associated with warm and cold fronts, and lastly identify the characteristic slope of warm and cold fronts. Here's just an example of different scales of different weather and global phenomena involving the size, right? Size in terms of how large they are on a global scale. We can talk about long waves, insolation, heat, re-radiating back into the surrounding area. Remember, our atmosphere heats from the ground up. We can talk on a synoptic scale. Synoptic is kind of the mid-latitude fronts. They're large scale, but they're not quite as large as a global scale. Also, hurricanes and tropical storms kind of fall in that. We can talk mesoscale. Those are thunderstorms, land breezes, etc. On a scale that's larger than a microscale. And then we can talk about small turbulent eddies. Notice tornadoes are kind of at the lower end of the mesoscale. Notice at the bottom, your x-axis identifying time. Some of these last from seconds to minutes, the microscale, versus the days or to weeks or even into months, where we're talking about long wave radiation. So we're really looking at the size and the time in which events take place on Earth that affect the meteorological conditions of an area. So here we're going to talk about fronts, boundary that separates air masses of different densities. Air masses retain their identities. Remember, a continental polar is going to maintain its properties, and where therefore a maritime tropical that comes out of the Gulf is going to maintain its properties and retain its identity. Notice warm air is less dense and it rises, it is forced aloft, and cooler air is denser and it acts as a wedge. It's literally pushing up, it's forcing up, driving up the warm air even at a greater rate than it would want to go. So here we have four types of fronts. Warm front, warm air is invading cold air. Cold front, cold air invades warm. Stationary, neither air mass is moving toward the other. It's kind of a static location. And then last but not least, an occluded front, which is a little bit more of a complex system. Cold air overtakes warm air and it rides underneath it. We'll look at that in a diagram shortly. Warm front, I want to make sure we realize that warm air is replaces cooler air. This is the cloud pattern that we'll be able to identify here in just a moment. This is shown on a map lined with semicircles. It's typically red. It's kind of a nice color code. Warm we associate with heat, so warm front. Has a small slope, right? It's just a very moderate or gentle slope. It's 1 to 200 roughly. So 1 unit per 200 over, so a rise to run. Clouds become lower as the front nears, and it's a slow rate of advance. Typically warm fronts come with longer duration rain, but it's only a light to moderate precipitation pattern. We have cirrus clouds. If we were out in front and a warm front were moving through, we would see cirrus clouds, cirrostratus clouds, altostratus, and nimbostratus. And nimbo identifies the precipitation and moderate precip at that. The warm front here, we talk about warm air is what's doing the moving. It's moving aggressively, faster than the cold air, so it catches up, and this is where we get our interaction at the frontal boundary. And there's just a cloud sequence that we've already identified. Cold front is identified by blue and with triangles. Here in this case, cold air is replacing warm air, shown on a map with line with triangles. That's what I just kind of mentioned a second ago. It's twice as steep, so its ratio is a 1 to 100, right? The rise over run. As a warm front, it's twice as steep as a warm front, excuse me. It advances faster than the warm front, so the cold air is advancing aggressively into the warm air. And the associated weather is more violent than a warm front. We can talk about the intensity of precipitation is greater and the duration of precipitation is shorter. So it can be a heavy duration, could be a thunderstorm, could be a tornadic activity, but the nice part about it is that it's kind of a short duration of time. Here we talk about the weather behind the front is dominated by cold air. Air is sinking or subsiding in this case, and after the front has passed through, normally conditions clear up. The cold front itself, it is the cold air that's moving aggressively into the warm air mass, and this is where we denote the cumulonimbus. These are the severe weather potential clouds, and we can also talk about cumulus clouds. Those are the fluffy clouds that look like pillows. They're typically out in front of storms that are developing. The cold front, though, when a cold front comes through, normally there's quick changes and it has the potential to get severe. It is important that we make sure we look at this picture here. You'll notice wind direction changes. If you can see the pictures in here, out in front, it's coming from the southwest, and then when the storm comes, notice we get a direction, an immediate changing in wind direction. And that's a result of, we've got warm air that is rising. It's fueling, the warm moisture is fueling the anvil shape to the cloud of the cumulonimbus. And we have the cold air that's wedging itself underneath, and this is where we get our lightning and thunder and the potential for tornadic activity. So here we're looking at the different types of weather that are associated with the fronts and also the cloud patterns themselves. Stationary front, flow on air of both sides on the front is almost parallel to the line of the front. The surface position does not move, and that's what's being held stationary. Lastly, the occluded front. These are a little bit more complex. Cold air is wedging the warm air upward, right? These are active, where cold air is under, well, it says overtaking, but technically it's moving underneath warm air. And weather is very complex. I want to make sure we emphasize the complexity. And precipitation is associated with warm air being forced aloft. Here's a picture of the occluded front. You'll notice in the picture, cold air is pushing warm air up. In the cold front, in the picture at the top, the occlusion takes place where the boundaries collide, and we get this kind of this unique pattern of weather in here. You can get a broad range, heavy rain, you can get hail, and you can have all kinds of conditions. Even tornadoes can take place at different locations here. But as it evolves and it moves forward, it just kind of comes and goes and moderates itself, and then takes off and heads on to the latter part of the evolution, where this cold air here, this cold front, this case, is just going to keep on moving forward. There you have it.